So it's very much work in progress that I'm doing with Tom Coates and Liana Heuberger, and also Giuseppe Pitton, who I don't think he's talking at this workshop. So we're taking the ideas that we've developed over the past few years in Fanosearch, and we're beginning to explore the terminal Q factorial Fano threefolds from this viewpoint. And, you know, at the moment we're just messing around and trying to find out things. So Liana will tell you a little bit more concrete maths, I think, in the next talk. Not messing around, exploring, enjoying ourselves. So, like I say, I thought it's safe to assume that nobody knows anything. So I'm just going to begin with a little bit of background. So we're going to take X to be Fano, the dimension I'm going to denote by n, and then associated to this, and I can't tell you an awful lot about this, is the regularized quantum period. Okay. And this is just a power series. Which looks something like this. And these coefficients here, these are counting curves of degree d on x. It's Gromov-Witten curve counts. Okay. And so really the only thing I want to say about this, although it's the key player in this talk, it's very hard to compute. Okay. And just to solve, it's going to be a reoccurring example, assuming I don't run out of time. So if we just took projective space, fortunately in this case, this isn't so hard to compute. Giventhal tells us how to do this. And just to give you a feel for these things, it looks like this. And just up here, I want to highlight this n+1 that's appearing here. This is the Fano index, making an appearance. Okay, so on the other side of the mirror, let's let f be a Laurent polynomial. Okay. Associated to this is what we call the classical period. So this is given by a certain integral, which I'll write down for completeness. But the important thing from our point of view is that it's very easy to calculate its expansion. And it looks like this, where these coefficients are just the coefficient of the constant term of the Dief power of f. Okay, and so the nice thing is this is easy to compute. If you haven't seen this before, you kind of know where this is going. On one hand, we've got something that's easy. On the other hand, we've got something that's hard, and we want to equate the two. But anyway, let me just continue with my example until I notice I'm really running out of time. So if I just take this Laurent polynomial, okay, then the constant coefficients are not very difficult to calculate. If you think about this for 1 second, you know, you're going to need to cancel off using this term here. And so it's going to be 0 if d doesn't divide n plus 1. Otherwise, it's just a nice little multinomial. So this is if d is equal to m plus 1 times by k. And to save you having to think about this, this is what that multinomial expansion is. And so we have that this classical period is equal to the quantum period of Pn. Okay, so that motivates the following. So we say F is mirror to our Fano X when this holds. And our hope is that it's possible to classify the F's, and this is going to be easier than classifying the X's. Okay, so that's our hope. And I'll also say that if someone hands you an F, you can try and reconstruct X from this. So I'm not going to go into this in this talk, but I think Liana is. So there's techniques such as Laurent inversion, allows us to reconstruct X from F in nice cases. Okay. All right. So I do want to introduce a little bit of toric geometry, but not much. So example continued. So if maybe what we saw above isn't that surprising, because let's let P equal to the Newton polytope of F. And to keep things simple, I'm going to do F is just equal to X plus Y plus 1 over XY. So the two-dimensional case, P2. Then we have XF. I'm going to define to be the spanning, the toric variety with spanning fan given by P. Okay, and so in our case we have P is equal to this little triangle, and this is going to give us the fan, which is just going to be this fan, and we see that XF is just equal to P2 as a toric variety. So maybe it wasn't such an amazing surprise. And indeed, our expectation is that if F is mirror to X, then the toric Fano variety XF is Q-Gorenstein deformation equivalent to X. Okay. And I'm guessing that Andreas talked about this a little bit. And in particular, and I mention this just because it's going to be one of the things we're going to be looking at. In particular, it means they have the same Hilbert series. And of course, by extension, the same anti-canonical degree. Okay. And I think it's sort of worth pointing out again, because this is toric, this is easy to compute. Okay, this is just the standard computation in polyhedral geometry. And so it's useful to have these Q-Gorenstein deformations, and we call these toric degenerations.
You just mean the Hilbert series?
Yeah. Okay. So I think I'm going to skip over the Picard-Fuchs operator and push on. So I can reintroduce it at the end if there's time. So section 2, I don't know if I labeled the previous section. Oh, I did, good. So section 2, I want to introduce mutation. Okay. So I'm just going to do this through an example. So let's consider some Laurent polynomial in n variables. Okay, and I'm going to pick another Laurent polynomial in just one fewer variables. So it's in n-1 variables. Okay, and let's suppose that maybe after making a monomial change of basis, so after a monomial change of basis, we can write our original Laurent polynomial in this format. Here's the thing. So where each of these pk's is equal to f to the minus k rk for some Laurent polynomial rk for all negative k. So what I'm trying to say here is I'm trying to say that whenever k is negative, we have f to the minus k divides pk. So that's the key thing I'm trying to say. So assuming that we can write it in this form, let's define mu f to just be the map from x1 to xn going to x1 to xn minus 1, and then f times xn. Okay, so then we can apply this map to our Laurent polynomial, and by construction we're just going to get another Laurent polynomial. So in the negative powers of xn, all we get is this remainder term, and if for the positive powers of xn, we're going to have to multiply through by a copy of capital F. Okay, and so by construction, this is a Laurent polynomial, and it's not too hard to check that this has exactly the same classical period. Okay, so this is a Laurent. This is the key thing. So in other words, if f is mirror to x, then g is mirror to x. And our expectation is well, I'd have said this was a conjecture until not too long ago, but I'm not completely sure about this. So, oh, I should say we call this a mutation. Sorry. So let me just say this. So we call this a mutation. So if F and G both have the same classical period, then what we expect is that there exists a sequence of mutations that sends one to the other. Okay. And let me see, how are we doing for time? Okay, I think this is fine. Let me just do one example. The only example of a mutation I'm going to do, just to make this concrete. So let's start with our mirror for P2 again, and let me just change coordinates. So I'm just going to write it as 1 over y plus 1 over xy plus xy squared. So I've made the transformation. X went to 1 over capital Y, and Y went to 1 over capital X, capital Y. Okay, so I'm going to take capital F, the factor, to be 1 plus X, and this gives a new Laurent polynomial G. This is going to be 1 over capital X, capital Y, plus X, 1 plus X squared, Y squared, just plug it into the formula. So changing my coordinates back, looks like this. And then, as it were, homework, draw the Newton polytope of this. And what you'll find, we have the toric variety P1, 1, 4. Okay. And in general, if F and G are mutation equivalent, then XF and XG QG deformation. And the expectation is that the converse is also true. So now let me introduce the star of the show, I guess, which is the rigid maximally mutable Laurent polynomials.
Can I ask something? I'm sure I've asked you this before, but if you have two toric varieties that have the same Hilbert series, you don't expect them to be related by a sequence of mutations, right?
If you have two
toric varieties that have the same Hilbert series, but not necessarily the same period.
Not.
And I think you have an easy example for this, right? An easy counterexample.
Yeah, sure. Well, in fact, I'm about to do one.
Okay.
Yeah.
Go ahead.
Yeah, because I'm about to do the example, which maybe Andreas already done today, the cone over dp6, where you have the same toric degeneration, but there's ways of getting two completely different period sequences. And so there's two different Laurent polynomials.
Sorry to interrupt. Can you hear me?
But those
is that you, Andreas?
Hilbert series, though, no?
Yeah, exactly. The question of Liana, I don't know what she meant exactly, but the question could be, there exist two toric, possibly singular toric Fano with the same Hilbert series, but they are not in this, they cannot be connected with...
and they're not in the same deformation family.
But just take your two Laurent polynomials in this case, just mutate them a little bit away. Yeah, so you've just moved along the deformation component a little bit. And then you'll have two toric varieties that aren't connected via.
But they have the same Hilbert series.
Yeah, they have the same. Isn't that maybe?
And
I'm
they're not. Yeah, no. This is okay. Yeah. I think I wanted an example where they're not even in the same deformation. Like they're not even in two different components of the same deformation family.
Okay, I don't think that makes sense. Okay. I don't think that's possible by definition. So maybe, because actually we're not doing too badly for time. So maybe if I can just come up here and just, since Liana's raised the question, does this expectation, if we have two Laurent polynomials that have the same period, then we expect them to be mutation equivalent. This is something that I think we really sort of take as an article of faith, but I don't know. I'm talking to you today about exploring threefolds, but we've been playing the same game I'm describing today in 4 dimensions, and maybe we've got a counterexample to this. I'm not quite sure about that. But that's part of the fun. Okay, so I'm going to draw a nice little, well, let me call this an example. I'm going to draw a nice little polytope in 3 dimensions. So let me draw a hexagon in its base. Okay, and then up here I'm going to draw the origin, and then up here, let me not be crazy, let me call it 0, 0, 0. So this point here is going to be 0, 0, minus 1. Then up here, I'm going to draw 0, 0, 1. I'm going to take the convex hull of everything in sight. Of course. So it looks like this. And then the points of this polytope naturally lie on 3 layers. So down here, graded by the z coordinate. So we have the z height minus 1. Then in the middle, we have the origin. Then at the top, we've got this single point. Okay. And so the question is, how can we turn this into a Laurent polynomial? So how can we assign coefficients to the monomials xu, u a point at the polytope, to get a good Laurent polynomial? So by good here, what I mean is something of geometric type, something that is supposed to give me the period sequence of a Fano variety. Okay. Well, there's a few things we can say to begin with. So because we took the regularized period, this means that we can assign coefficient 0 to the constant term. Okay, so if I start labeling my coefficients, I get to assign coefficient 0 to the origin. And then there's a certain degree of freedom given to us by the Picard group. And this allows us to place 1s at the vertices. Sorry, I've been a bit sloppy there. What I mean is it allows us to assign the coefficient 1 to the monomials corresponding to the vertices. So I'm going to get 1, 1, 1, 1, 1, 1. But I don't know what to assign to this point here, 1 over z. Okay. So what about So what we want to do is we want to think in terms of mutation. And if we think in terms of mutation, we think about the hexagon on the bottom, where this 1 over z is living. And we think, what are the possible mutations we can do where we're dividing through by a factor f down here? Okay. And it turns out there's exactly 2 different ways we could do a mutation. So notice that there are 2 Minkowski factorizations of the hexagon dp6. So let me just draw them out for you. So with respect to some choice of basis, here's my hexagon. And the first thing I can do is I can just Minkowski decompose it into the sum of 3 line segments. Which I think look like that. So that's possibility 1. And the second possibility is to Minkowski decompose it into the sum of 2 triangles. Like so. Okay, and so this gives me 2 completely different mutations. What you need to do is you need to, go back to that formula that we had above, and you need to choose capital F to be one of these Minkowski components, and then you need to see how that limits your choices for the Laurent polynomial A. So you go through this. So in the first case, I'm just going to set f equals 1 plus x. And if you work through the definition of mutation, you see this forces A to be equal to 2. There's just no choice about this. Okay. And in the second case, set it equal to the triangle 1 plus x plus y. This forces A to be equal to 3. Again, there's absolutely no choice about this. And you can go away and you can calculate the period sequence in each case. So in the first case, it's 1 plus 4t squared plus 60t to the 4 plus ... And you can look this up, and this corresponds to a 1-1 intersection in P2 cross P2. And in the second case, it's 1 plus 6t squared plus 90t to the 4 plus ... And this is just equal to P1 cross P1. Andreas and Judah, am I right that you discussed something similar to this morning, or?
You did it in the affine case.
Right, okay, good. So what we're seeing here is that choices of coefficients somehow see the Q-Gorenstein deformation components. Okay. All right, so now let me introduce these maximal mutable Laurent polynomials. So let GF be the mutation graph of a Laurent polynomial f. Okay, so f is called a maximally mutable Laurent polynomial if for every G with Newton polytope agreeing with F, and such that G's mutation graph contains F's mutation graph, we actually have equality of the mutation graphs. Okay. So all I'm trying to say here is that you can't fiddle with the coefficients of F and find some mutations that you didn't already see. Okay. And then in addition, we have sorry, let me try and write this in better English. So if in addition we have that the Newton polytopes agreeing and one mutation graph contained in the other mutation graph, then this forces not only the mutation graphs are the same, but in fact the Laurent polynomials are the same. Then F is rigid. So there's different ways of saying the same thing, okay, and not really settled yet on the right way of saying this, but this is one way of describing the objects that we're interested in. And the conjecture is that rigid maximally mutable Laurent polynomials, so those Laurent polynomials that are uniquely defined by the set of mutations they support, this is in one-to-one correspondence with terminal Q Fanos. These are up to QG. And also, when this is the case, then we expect that the classical period agrees with the quantum period. So these are the mirrors. Okay. So this is the this is the main thing driving our experiments. On the one hand, we have things that we can construct explicitly by just playing around, and then on the other hand, we have things that we don't really know, and we hope to be able to explore what's going on in this way. So for exploring the landscape. So I'm running massively under time. Turns out that writing on a tablet is much faster than writing on a board. So you should all probably point out that I'm going too fast. Okay, so what are we trying to do? So our aim is to understand the database that Miles and Gavin and Kari Suzuki and others developed of possible terminal Q Fano threefolds Hilbert series using this technology. So we want to understand the graded ring database of Q Fano threefold Hilbert series. Using rigid MMLBs. Okay, so there's a little bit I need to say about this. So if you go onto the graded ring database, then you'll quickly find this list of Hilbert series. Not all of them necessarily exist, so that's complication one. Okay, you have to be a little bit careful, and you have to study each example and figure out whether they exist or not. Okay, and complication two is most of them are outside of the world in which we can so far hope to find toric models, but that's something I think we can fix in time. So what we're going to use is existing classifications of lattice polytopes, of Fano polytopes. So in particular, again, you can find this on the graded ring database. There's approximately 600,000 so-called canonical polytopes. And at least to begin with, these are the examples that we're going to be working with. So I've got to say, let me say this in a different color. Here, if I'm remembering correctly, there's around 50,000 Hilbert series. Okay, and here, if I'm remembering correctly, there's only around 3,000 Hilbert series. So already you see that we're certainly not going to be able to find a toric degeneration for everybody in the QFano threefold database. But there are other classifications of polytopes that we can construct that sort of will be able to fix this problem. Okay.
I mean, first of all, there may be some that don't exist, but also, isn't there also the problem that maybe in the mutation class, there is nobody who is canonical? Can that happen?
I mean, yeah, of course, like I say, okay, so let me sort of say this as an aside, you know. So these are lattice polytopes P with one interior point. And there's absolutely no reason whatsoever to expect a given QFano threefold to have a QG degeneration to one of these toric varieties. No reason whatsoever, okay? But we can also classify P with two interior points, etc., etc., etc. Now, what you can do is you can plot a little graph. Oh, I wish I had it in front of me so I could show you, but I don't. But you can plot a little graph of the data that's in the GIDB. And for the sake of argument, it looks something like this. And then you can plot a little graph of the data that comes from these one interior point polytopes. And I'm not lying too much when I say it sort of looks like this. And then if you plot a graph of two interior points, it sort of looks a bit like this. And so I have no theoretical reason for this, but you can sort of imagine that you could figure out that there really is a cutoff where once you've calculated all, all polytopes with n interior points, you've probably found a toric degeneration for everyone in the GIDB. Okay, I mean this is experimental, right? There's no maths behind it.
Is the blue part the QFanos, or is the blue part the?
This is meant to be the Q.
Oh, yeah, the QFanos. Okay, thank you.
This is really an aside. So the hope is that we can begin populating the landscape. So I really want to emphasize that we're only exploring for now. But what have we done? Well, we've worked through about 90% of the canonical Fanos, and we've sampled those for maximally mutable Laurent polynomials. And so these have yielded, whoops. So these have given us approximately 100,000 rigid maximally mutable Laurent polynomials. So conjecturally, these are given us mirrors for a whole bunch of Q Fanos. But these in turn give just isn't. This has given us approximately 8,100 distinct periods. Okay, and these correspond to approximately 1,100 distinct Hilbert series. So using this technique, this means that we've covered about 2% of the graded rings database using this method so far. Okay, I mean, that's the negative spin on it. The positive spin is that we, in theory, we might have found 8,100 Q-Fano 3-folds when Liana applies the ramp inversion.
Where's the other 2,000 Hilbert series? I mean, they were distinct above, right, when you listed the canonical?
And the canonical people, many different canonical people can have the same Hilbert series.
Yeah, but you said there's about 3,000, I guess, unique of them, right? You wrote 3,000 there.
Oh, yeah, but, okay, so,
sorry.
It does say about. Does say about. No, that's not as wrong as it sounds. No, I think that's right. Many of them won't give us a rigid maximally mutable Laurent polynomial.
All of them match a Fano?
So many of them will give us a maximally mutable Laurent polynomial that isn't rigid. Okay, so in other words, that doesn't correspond to a terminal Q-Fano. Okay, and actually, yeah, this is the sort of hint, right? There's 600,000 canonical Fanos, polytopes, okay? But we've only found 100,000 rigid MMLPs. So that means that, about 5 out of 6 of them aren't given a rigid MMLP.
Mm-hmm.
Okay.
So just to put that in context, Gavin and I and our school have managed to construct about 200 of these or 300 of these with some confidence. And, we could perhaps work on for another, couple of generations of graduate students and get another 100 or so. But that's the limits of our methods.
Yeah, no, that's a nice comment.
Yeah,
Thanks.
thank you for the encouragement, man.
Okay, so now, so far so good. I hope nobody is too disgusted with what I've said. Now this is where you've got to hold your nose if this offends you. I'm so sorry. So, can we see structure in this data? I think this is fun. Okay, so how are we going to find structure in this data? I don't know. I don't know what I'm looking for. So we turn to the thing all the cool kids are using. We use machine learning. Okay, so I want to say a couple of remarks about machine learning. So machine learning is a fancy title for something that basically just boils down to a whole bunch of linear algebra stacked on top of linear algebra. Okay, it's not actually anything too extraordinary. And I think as a pure mathematician, if you go away and you start studying machine learning, you're going to become a little bit disillusioned with it. It's essentially linear algebra at a big scale, but it still produces nice results and it's still very interesting and it can do some serious things. There's limitations about the sort of data you can feed in, obviously, and there's limitations about the sort of things you can expect to come out. But period sequences are perfect for machine learning because period sequences are just sequences of numbers. And that's exactly the sort of thing that machine learning has been designed to look at. And so we just basically, for now, we're exploring, we're just playing a game. We're trying to get the machine to match up period sequences with geometric invariants, and we want to see what drops out. Okay. And for a lot of this work, I've really got to say, it's Giuseppe Pitton and his incredible ability to play with this data that's found all of this stuff is really, really nice. Okay. So the first thing is we used, I think at this point actually I need to move to some pre-prepared notes. So let me just skip across. Okay, so the first thing is to use principal component analysis. I only know what Wikipedia says about this, but principal component analysis gives us a way of taking these period sequences, which, well, we only recorded the first 15 terms of the period sequence, so you can think of them as just points in 15-dimensional space, but it gives us a way of projecting it down to, well, originally to 3-dimensional space, but then it turns out we can nicely project it down to 2-dimensional space. So what you see here, okay, this is a result of the projection that machine learning has suggested for us. So every single point here is a different period sequence that we found that allegedly corresponds to a terminal Q-Fano threefold. And most of them lie on this. And although you can't really see it in this picture, this really is a 2-dimensional wedge. So what you've got to imagine here is that there's this nice 2-dimensional wedge where most of the period sequences lie. And then in 3-dimensional space from the projection, it sort of explodes into this slight cloud of period sequences around here. And although I haven't got a graph of this, which is a shame, if you colored all the period sequences that have Fano index 1, they're all sitting along here. And then if you color the higher Fano index, they're lying in layers out in this cloud. So there's definitely some structure. Okay. And so what happens if you focus on this wedge and you start slicing by things like Gorenstein index? Well, here I've got 3 graphs, 1, 2, 3. So what we've done is in this first graph here, we've sliced by Gorenstein index equals 2. So we've only recorded those period sequences that, according to how we've matched them up with Miles and Gavin's and Kari Suzuki's database, these have Gorenstein index 2. Here's Gorenstein index 4, here's Gorenstein index 6. And we've colored the period sequences according to their Hilbert series. So unfortunately, the machine's done this and it's done it in a not very nice way. But so it's quite hard to actually tell the difference between the colors. But you know, along here, all of these period sequences have the same Hilbert series. They're the same color. And here's another bunch of period sequences with the same Hilbert series and another and another. And well, you know, you can see for yourself, they're all lying in lines. And so, you know, what you can imagine you're seeing here is each of these lines corresponds to, well, each of these points corresponds to components of the QG deformation space. Okay, and then this line corresponds to the entire QG deformation space. Okay, so maybe, you know, we can figure out the details of what's going on, how it's bounded, why there are a few points that seem to be missing. Maybe then you could even hope to be able to say something about completeness of these results. I'm not sure. Okay.
There's a question in the chat.
Oh, good. So what does it say?
It says, are the smooth panos showing up in an interesting way? I'm guessing it's in these graphs.
Right. So they do show up in an interesting way. The smooth guys live along this edge here. Except for 1 or 2, which then just lie a bit randomly. You know? But yeah, the smooth guys are sort of mostly living along this edge here. Okay, and so the next thing that you can play with is this. Can you predict the degree from the period sequence? You know, the degree is a QG deformation invariant, so it should be possible to do it. And it turns out that neural networks can do this incredibly well. So you see here this graph, you know, along the bottom is the actual degree, along the side is the predicted degree from the neural network, and given only the period sequence, in fact just the first 15 terms of the period sequence, to a really high degree of accuracy, the neural network is being able to tell me what the degree of the corresponding Fano threefold is. I mean, I think, you know, one expects that one would be able to do this. I don't have the foggiest idea how you actually do this. And so the next fun thing is, well, okay, Hilbert series, you know, associated to a period sequence is a Hilbert series. So can it calculate the first few plurigenera? And the answer is yes. You know, again, you see it here. So exactly the same. Along the bottom axis is the actual value. Along the side is the machine prediction. All it was fed was the period sequence, and it's managed to correctly guess the terms of the Hilbert series.
But how did you have the period sequence to feed it? Like, how did you know it was the period sequence of the, so you already had the answer before you plugged it into
Yeah, we
this?
already had the answer because we started with a known polytope, a known toric variety.
Okay.
Okay, so we already know the answers to these questions.
So can it do the reverse somehow? Like determine
Yeah,
if
of course. I mean, I think that's what the fun thing here is, you know, you could now give us a period sequence and we could ask the machine to guess what its Hilbert series and what its degree is. I mean, okay, you know, you can see there's a sort of cloud of accuracy. It's not giving it on the nose, but, you know, that's still
but
so much better than what we already knew. Yeah. And then I think this is the final one. Yeah. And next thing was, can we machine learn the rank of the Picard group, or, you know, modulo a little bit of manipulation? This is the degree of the Picard focus operator. And, you know, I think this is still quite a nice, convincing result. It's not as nice as the other ones, but it's still pretty good. And let me just emphasize why this is quite remarkable. So the Picard focus operator, I didn't go into it, but you calculate it from the period sequence. Okay. So you maybe, and it's all just a bit of linear algebra applied to a period sequence. The thing is, to actually do this correctly, you need hundreds, even thousands of terms of the period sequence, way more than we can ever conceivably compute. Whereas here, the machine is pretty accurately guessing the degree of the Picard focus operator, the Picard rank, just from 15 terms of the period sequence. So if you're prepared to sort of have a little bit of faith in what the machine is giving you, you know, this could really speed up doing these calculations.